Okay, welcome everyone. Today I'm doing a problem on the whiteboard. Here is the problem on the screen. I'll read it out for you guys without any interruptions. It's two sentences. The index of refraction for violet light in silica flint glass is 1.66, and that for red light is 1.62. What is the angular spread of visible light passing through a prism of apex angle 60 degrees if the angle of incidence is 50 degrees? And we have an image here. I'm gonna draw the image up here and leave all the stuff I write up here so you can refer back to it. But basically we have a prism. Apex angle is this angle all the way at the top. This is 60 degrees. And the question is asking, what is the angular spread of, let's see exactly how they word it. What is the angular spread of visible light passing through a prism? Okay, what is the angular spread of visible light? Question mark. So I will call that angle of spread theta, and I'll do subscript spread over here. So we have a number over here. We can put it in degrees. We can put it in radians, whatever, if it's an angular unit. And if we put a number in here, that should solve the problem. But let's figure out what the problem actually is, because it's a little bit confusing the way it's worded. And actually, I think it's pretty important to draw a little bit of what's going on here in different colors. So I only have blue and green here. So I'm going to draw, I guess, we'll see how we draw it. But over here we have a dotted line, which is normal to the prism surface over here. Normal means that this dotted line is at 90 degrees with respect to this side. And we're told some information about light entering here. So I'll draw this black line with an arrow over here and call this white light. This is coming in and hitting the prism at an angle 50 degrees to this normal. So by the law of refraction, since we're entering a different medium here, I'll actually draw this in blue. This is silica flint glass. It has a different index of refraction. We will do N. For now, we don't really know what it is. Actually, they told us two different indices of refraction, but based on the law of refraction, or Snell's law, which I'll write down in just a second, this light over here refracts and it does not follow the same trajectory. So if I were to draw a dotted line of the trajectory this light takes, if the prism wasn't there, it would go somewhere over here. This is the undeflected light ray. Since it's entering the prism at this point here, we have a splitting of the white light based on each of the colors of the visible spectrum. So I'll draw one over here, maybe it's like that, and I'll draw another one over here, maybe it's like this. So these are two different rays of light, and within this little band here we have the whole rainbow, right? Because each color or each wavelength of light refracts at a different angle, depending on the wavelength of light and depending also on the material. So in the problem, they actually give us the index of refraction for the material. They say that it is 1.66 for violet light and 1.62 for red light. So I'll do lowercase n, index of refraction, vio for violet, 1.66. And we have another one, index of refraction for red light, 1.62. So I'm not sure which one is which. Maybe the blue here is the violet ray and the green here is the red ray. We'll see. Apologies for not having the proper colors here. But anywho, this is what happens theoretically. Light ray comes in, boom, splits into its two different, or all of the different colors of the rainbow, depending on the index of refraction. And over here, when it exits the prism, it actually refracts again. I don't know exactly which direction. I'm just kind of drawing a random ray direction here. And it refracts again here. And what we see here is a rainbow. take a look at the Pink Floyd album, the one with the prism. You'll see a rainbow appearing after you shine white light into a prism like this. And right over here, you could see the rainbow. Rainbow. I'm not sure which color is at the top. Maybe it starts with red up here, red, orange, yellow, green, blue, violet, indigo, whatever. Or maybe red starts here. I'm not too sure. We're going to find out as we work through this problem. But this spread over here is an angle. So you could call this theta spread. So this is very good because if I have this and I plug it into here, I can solve the whole problem. So it's good to kind of do that a little bit. Actually, in the picture, they give us a bit more information. They tell us that red is up here. So they draw this as red. Again, I apologize for the colors that I have here. Don't stress about it though. Even if you have a black or blue pen, just draw this picture. Keep some stuff in mind. You can label some things. So we start with red and we go down, red, orange, yellow, green, blue. And I think this is the violet ray, viol. So the problem is, what is the angular spread of visible light? Visible light starts with the red color in the rainbow and it ends with the violet. If you go further this way, you get into some other light rays that are not visible to the human eye. And if you go further this way, you have some other invisible to the human eye rays. So this is the rainbow, the visible light, and this right here is the angular spread which we are looking for. That's what the problem is asking us. Alrighty, if that feels good with you guys, I'm now going to write the main equation that we're going to use, which is Snell's law, also known as the refraction law, because when the light enters this point here, this separation of two mediums, it refracts, and the way it refracts obeys Snell's law. So this is what Snell's law looks like right here. N1 sine theta 1 equals N2 sine theta 2. This is the angle that the light makes when it first touches, when it first interacts with this medium, or this kind of boundary between two mediums. So we actually have that. That's 50 degrees right here. I can label this as theta 1. Theta 2 is the angle at which the refracted light is going at. So we can draw another normal axis right here, and we can find theta 2, which is here or here, depending on which ray we're looking at, the red ray or the violet ray. N1 is the index of refraction of the outside. So normally we take the outside to be air. N1 is equal to 1.00. And the inside is silica flint glass, and they give us two indices of refraction for each type of light, for each color of light. This is actually an important rule here, which I'll just draw very quickly. If I plot the function index of refraction as a function of wavelength, which is lambda, and I plot wavelength over here, as you increase in wavelength, the index of refraction normally decreases like this. And you can have different materials here, but normally they slightly decrease like this. So this could be for different materials. Let's say some type of glass. Let's say this is some kind of oil. Let's say this is some kind of honey. I don't know, different materials. You can look at this plot somewhere online depending on what material you want. But generally, I just want to show you that as you change the wavelength of light, the index of refraction also changes. So that's where this is coming from. Red light has a different wavelength than violet light, and therefore it has a slightly different index of refraction. And because of that, and because of Snell's law, the angle of refraction for each of the light rays here is going to be different. So overall, in general, that's what gives you the rainbow. So that's some preliminary information, which I'm going to leave up here. And now we're going to get to solving the problem. So keep in mind what the problem is. Theta spread. Always keep that in your mind. That's kind of where we want to be pushing towards. And since I kind of have a diagram there, but it's a little bit cluttered, I'm going to just draw a big diagram here. This is my prism, 60 degrees. I have the point where the white light is entering right here, which I called this theta 1, 50 degrees. And what I want to find now is, let's start with the red light. I will put red over here, dot dot, and an underscore. So we're going to do the solution for the red light here. Basically what we do is just write down Snell's law again. N1 sine theta 1 equals N2 sine theta 2. And we could just plug stuff in that we already know. So we know that the first index of refraction is 1 because the light is entering from air. Air has an index of refraction of 1. And we can continue on with the equation sine. The theta 1 here that the sine eats is the theta here, the angle that the light is making with respect to the normal of the surface. So you want to make sure you draw this normal properly. And we saw that that was 50 degrees. That was given to us in the problem. So everything on the left-hand side we know. We can just fill it in there. Index of refraction N2 is the index of refraction of this material with respect to the red light. So we can plug this number here, 1.62. Let me actually confirm that is the right number so I'm not like doing anything incorrectly here. Red light, 1.62. Violet light, 1.66. Cool. 1.62 sine. And then here we have theta 2. This is the only unknown. And if we find this, we're going to find the angle over here at which the light is refracting. Cool. So this is the unknown that we have to isolate for. How I can isolate for it is divide this 1.62 on this side. So I'll do that in steps. I got 1. Actually, 1 multiplied by anything is just the same thing. So I could just omit this 1 over here to simplify things. In the numerator, I have sine of 50 degrees. In the denominator, I have 1.62 equals sine theta 2. Theta 2. Cool. I again want to isolate for this theta 2. And how I can do that is I need to cancel this sine over here. So I can take on both sides of the equation sine inverse. Sine inverse of this side, sine inverse of this side. Sine inverse of sine of theta cancels the sines because sine inverse and then sine are inverse functions, so they can cancel each other nicely. So on one side of the equation, I have isolated for theta 2. On the other side of the equation, I have sine inverse. And inside the sine, I have sine 50 degrees divided by 1.62. Boom. And this I can plug into a calculator because everything I have is known. So let me pull up a calculator. Normally I use my phone, but now I'm going to have to use Google over here. Calculator. All right, so we have sine. Let's work in degrees. Make sure your calculator is in degrees because we have degrees right here. So first I'm going to do sine of 50. Boom. The answer is 0.766. I will take that answer and divide it by 1.62 equals, the answer is 0.4728, blah, blah, blah. And now I want to take sine inverse of that. How do I do that? Sine inverse of 0.4728. Okay, I'm just going to copy this, copy. And then here I have inverse sine V. Oh, let me copy, control V. Damn, I can't control V. 0.7, 0.472867. Arc sine is another name for sine inverse of 0.472867 equals 28.22. So I can put 28.22. And what we have here is theta. So if our calculations are correct, this should be in degrees. Awesome. So take a look at this. We have an angle of 50 degrees right here. If we continue these lines, this would also make an angle of 50 degrees. And this angle of 28 is about half, like maybe a little bit more than half. So I can take this angle and kind of just draw a little bit more than half of that. And this I will call theta 2, which is 28.22 degrees. That look good? Alrighty. Nice. At this stage, we can kind of stop here and do the exact same thing for the violet. But what I'm going to do is just do everything for the red and then move on to the violet. So what I mean by that is the red light ray is hitting the interior side of this prism at an angle over here. I'm not sure what this angle is. I'm going to call it angle red, theta red. So I don't know what that angle is, but I need that angle in order to find how the light ray refracts and exits here. Because if I find the direction of the light ray on this side of the prism, I can do kind of the same thing for the violets. And if I have both of these angles, I can kind of do some algebra and find the theta spread here, which is going to be our answer. So let me know if you guys agree with that. That is my strategy here. And if you're good with this, I'm going to erase everything here and just try to find this angle so then I can find the final angle for the red. Cool. Make sure to do these calculations on your own. I can always make a little mistake using the calculator I've used here. So try to take a look at this problem on your own. I can for sure make a mistake, and I can make a theoretical mistake as well. So if you have another kind of strategy to use here, please feel free to use it. So okay, I'm gonna write again Snell's law equals n2 sine theta 2. Except now we're applying Snell's law at this intersection here. My bad. Let me turn on the lights over here. That might be a problem that occurs quite frequently, but I'm going to try to make this video with no cuts. Cool. So now we have Snell's law applied to a different section, which means the index of refraction here is now the one of the prism. So I'm going to plug that in. That is 1.62, right? Because again, we're using it for the red light. Red light has this index of refraction. I have here sine theta 1. I actually don't know it yet. It's this angle here, theta red. So I don't know what that is. I'm going to kind of just leave it blank like this and fill up the rest of the equation. So N2, the light ray is now exiting and entering the air again. So we have index of refraction 1 for the air. And here I have sine, and again, actually I'm going to do this as theta 2. Maybe theta 2 is not a good one because we've already used theta 2 here. I can maybe use the letter subscript F for theta final, if that's okay with you guys. So we're looking for this. This is what we want to find. But in order to solve for that, we actually need to find this angle here. So when you're looking at something like this, and you have some angles, and you have some lines and triangles, you want to try to find a triangle that can help you find this final angle. So try to redraw this picture if it looks a little complicated. Try to kind of explain it to yourself what we're looking for. We're basically looking at this angle here, the angle that this interior red light ray is making with the normal, interior normal of this prism surface. So I drew that and labeled it theta red here. Cool. Now what I can see is this big triangle over here. And I'm going to draw this triangle kind of like this. So this is the top of the prism. I know that this is 60 degrees, the apex of the angle. This angle here, I know that it is exactly 90 degrees minus theta 2. So why am I saying that? Because this dotted line is the interior normal. Remember how we define the normal? Normal is a line that is exactly 90 degrees with respect to the surface that it is normal to. So I have this box over here telling us that this is 90 degrees. And you can see that this entire box is comprised of two angles. This angle here, this small arch that I've drawn, and this angle here, which we found was 28.22. So how I can find this angle here is literally 90 degrees minus 28.22. Cool. Why is that helpful? Because now we can plug this angle into here. And if we have this angle and we have this angle, we can find this angle by a little rule that I've talked about previously on this channel, which is that all interior angles of a triangle add up to 180 degrees. So let me do this little calculation here and check out what 90 degrees is. 90 degrees minus 28.22. 28.22, is that true? gives us 61.78. So that is this angle here, 61.78 degrees. That is this over here. Nice. Now, if I have this angle here, which I will label X, I can find it by doing 180 degrees equals the sum of all of these angles. So the first angle I have is 60 degrees, this one here. I can add that to 61.78 degrees, and I can add that to X. Once I have all of this, I can subtract this on this side, subtract this on this side, and I can get what X is. Cool. Let's take a look, and if you're unsure why I'm doing this, it will become apparent in just a second. And if you can't kind of see the pathway, like why we need to do this, it is good to practice these problems. You'll kind of get your own inkling of why we need to find this. But okay, enough yapping. Let's do 180 degrees minus 60, minus 61.78 equals 58.22. 58.22. So that is X over here. 58.22. Why is this helpful? Because that gives us this triangle here, or this angle here. This is X, which I just found. And we can do the same trick as what I used over here. 90 degrees is equal to this angle plus this angle. On this side, you can see this big 90 degrees here. From the edge of the prism to this normal line, that's 90 degrees. And that is comprised of this angle which we're looking for, plus X. So overall, in summary, theta red here can be found by doing, I'll do theta red, 90 degrees minus this X, which was 58.22 degrees. Alrighty, and theta red is the thing that we're going to plug into here. And then we will be able to find theta final. So if that was a big leap, I understand. It is kind of a weird way of finding angles. But whenever you start working with angles, make sure you kind of visualize some triangles. If you have two triangles, or sorry, if you have two angles of a triangle, you should be able to move forward pretty good. So what are we doing here? 90 degrees minus 58.22. Gives us 31.78. And I'm just going to plug that in right here. 31.78 degrees. Alrighty, if that's good with everybody, I'm going to erase this. Here, erase this. I'll also erase this. Even though maybe I didn't need to. Okay, I won't erase that. I'll keep that there. And I'll erase this. And I'll just do 31.78 degrees. So this picture kind of is just talking about the red light ray. Alrighty, same thing we did here as the previous step. We're going to isolate for theta final. After you do this a couple times, you can see there is a pattern of how this looks. Basically, I'm just isolating for this. The way I isolate the sign is I take a sine inverse and I move this onto this side. If I divide by 1, it doesn't really do anything, so I just have this final equation here. 1.62 times sine of 31.78 degrees, sine inverse of that entire thing gives us theta final. And theta final is important, and maybe I will do a small prism here. So I have this light ray here. It is splitting into these two light rays. And I just found that one of these angles, so either this one or either this one, is going to be theta final for the red. I'm not sure which one it is because I don't know if the red light ray is above. Oh, I actually do. In the problem, it showed us that the red light ray is on top. So the angle here, theta F red, is actually this one. Theta FR is equal to this. And then this one down here is theta final violet. So if we find both of those, we can most likely solve the problem. And what we're working on here is just the final angle for the red. Alrighty, back to the calculator. Let's do sine inverse of 1.62 times sine of 31.78. 31.78. That gives us 58.56. Okay, pretty cool. I'm gonna just write that here. 58, what did that say? 58.56. That's pretty good. 58.56 degrees. I'm gonna maybe put that in a box right here because it looks important. And all right, if we've made no mistakes, I think we're good. I'm gonna erase all of this and do the same thing for the violet ray, and then we'll try to finalize this problem here. So I'll erase this. Actually, erase this too, and now do Vio. Maybe I can keep this picture here. Nah, it's getting a little cluttered. Let's just erase. Ooh, maybe there was actually some important angles to keep in mind. Anyway, if it's important, we'll head back to it. Probably best not to erase everything that you've worked on though, because if you made a mistake, you can go back and check where that mistake was. But in this case, I'm recording, so if I made a mistake, I'll take a look in the editing stage. All right, let's do it for the violet light. Same kind of procedure, figure out what's happening. So we have white light entering over here at 50 degrees. It then refracts at some angle here, and that angle we're going to find right now. So Snell's law again, this is the main equation that we use for the entire problem here. Sine theta 2. We're going to plug in everything that we know. So N1 again is 1.00, and theta 1 is again 50 degrees, right? Because the light ray is coming in and contacting the material at an angle 50 degrees to this normal, and it's entering from air, index of refraction air, which is everywhere around this prism, is 1.00. Then we have 1.66 for the violet light ray, and we're looking for theta 2, which is going to be the angle at which the light ray is refracting here with respect to the interior normal. So again, we can isolate the same way. Theta 2 is equal to sine inverse sine of 50 over 1.66. Again, I just removed this 1 because 1 times anything is that same thing again. And we are back to the calculator. Boom. So we have sine inverse. We have sine 50 degrees divided by 1.66 equals 30.12. Interesting. 30.12 degrees. So before we saw that it was actually around 28. So this is actually bending at a greater, hold on a second. This is a little bit strange. Because I remember the interior angle of deflection here for the red ray was 28 degrees, just from my memory. And now we're getting 30 degrees, which is a bigger angle. So that would mean the violet light, the violet light ray is above the red light ray. All right, at this stage, I feel a little bit weird. I feel like maybe I've made a mistake, but we are going to keep trekking through and just see if we get, I know kind of the general answer for this problem. So if we get the incorrect answer here, we might have to go back and make some changes, but it's interesting. So the main problem I'm having is we found this interior angle of refraction for the red ray first, and I remember it was around 28 degrees, about half, a little bit more than half of this 50. So I drew it around here, and now we found that the refracted angle for the violet ray is 30, which is a bigger angle. So if the violet ray is refracting at a bigger angle, it should end up above the red ray. But that's not what we're seeing in the picture. The picture gave us actually the rainbow, starting with the red. And yeah, for that reason, I feel a little bit uncomfortable with this. Let me just check the picture again, see if I'm messing anything up. Maybe I plugged in 1.62 where I should have plugged in 1.66 or something like that. Anyway, we're going to keep moving forward. 30 degrees. Awesome. Again, keep in mind that what we want to find at the end is the angle over here. This I will call theta final violet, and that is the angle we're going to put here, which is of importance. In order to find that, we need to do Snell's law with this angle over here, which I will call theta VIO. We want to find that. And how we find that is the same way as before. Take a look at this big triangle here. So I'm going to draw that triangle kind of like this. This angle here is the apex of the prism, 60 degrees. This angle here is this angle here. You see that? So this angle is exactly 90 minus 30.12. Let's peep that very quickly just to make sure my calculations are good. 90 minus 30.12, 59.88. Okay, 59.88. That is this angle here, 59.88 degrees. Cool. To find this angle, we have to do 180 minus 60 minus 59.88 degrees. So let's take a look at that. 180 minus 60 minus 59.88 equals 60.12. Does that make sense? 60.12 degrees. Okay, 60.12. And that is this angle here, 60.12, which allows us to do Snell's law again as the violet ray is exiting the prism. So let's plug in all this stuff again. Keep in mind that the problem now has switched. We're looking at this intersection here. So N1 is now 1.66 sine of, and the angle that we're looking at here is this angle, 60.12. Is that true? We'll see. The light ray is exiting, so N2 is the index of refraction of air, and we're looking for this angle, which we have renamed theta final violet. Cool. We're going to isolate for this, and we will isolate the same way as we always do. We have a sine inverse here. Inside the sine, we have 1.66 sine of 60.12 degrees. And the 1 over there, I will not write. All right, let's take a look if we got something interesting. Sine inverse, 1.66 times sine 60.12. Whoops. How do I backspace here? 60.12. That's true. Ooh. I'm getting an error. What the heck? Okay, let me retry that again. Inverse sine 1.66 times sine of 60.12. Error again. 60.12. Let me try sine of 60.12 on its own times 1.66. Huh. Okay, for sure something is wrong, because once you calculate this, just this interior thing, 1.66 times sine of 60, you get a number 1.49. And sine inverse can only take in things that are between -1 and 1. So this is why we're getting an error here. So something's wrong with this. Let's try to find out what the problem is. So for sure, this is correct, this 1.66. This is coming from Snell's law over here. The problem is this angle here, 60.12. So where we got this from was from here, 180 minus 60 minus this angle, which I took a look at from here. So 180 minus 60 makes sense. This is the angle here. 59.88 is the angle I got over here, which looks like this is where the trouble is coming from. I'm kind of just reverse engineering here what I did to see where this error is coming from, right? Here we got an error. We should have gotten some angle. So where did we get this 59.88 from? We did 90 degrees, which was here, from the prism to this normal, minus 30.12. And if you remember, originally, I was confused about this 30 because I remembered that the angle for this red ray should be bigger than the violet ray. And originally we got 28 point something for this angle. And now we got 30 point something for this angle, which doesn't make sense. Just look pictorially looking at it, this angle for the red must be bigger than this angle. So either I did something wrong with this, or I did something wrong with this, or maybe both. All right, let's try to figure out where the issue is. So how I found this angle was from Snell's law part 1, which is literally this law here. And I plugged in index of refraction of air for N1. I plugged in 50 over here, and I plugged in index of refraction for the violet light in the prism over here, and then I solved for theta 2. Let's just try that again very quickly. So I'll do theta 2 equals sine inverse. Then I have here 1.00 sine of 50 degrees. And on the bottom here, I have 1.66. So let's take a look. If I, let me turn on the lights one more time here. I know this video is kind of continuing on longer than it should, but you're seeing me solve some errors here in real time. Let's do that calculation. And if we get 30.12 again, we're gonna reassess and see where the problem is at. All right, so I have degrees sine inverse of, and what I have inside the sine is 1 times sine of 50 degrees. And then I have close that divided, oh, my bad. Let me erase that and do here divided by, oh man. It's not letting me do the divided by outside the sign because I'm using kind of a goofy calculator here. Okay. I'm just going to do sine of 50 degrees, close bracket, divided by, okay, I got it now, 1.66 equals, I got negative. What the heck is going on over here? So I just plugged everything in. I did arc sine of 50 divided by 1.66, and I'm getting negative 1.58. Oh, now it changed to radians. Okay, no. Please go to degrees. Okay, I got a new number, 27. Alrighty, this is looking good. Maybe I just made a calculation error before. It's 27, which is smaller than 28, which is exactly what we want. 27.48 degrees. All right, let's erase some stuff here. So this angle that I originally calculated was 30 is incorrect. I don't know where I made the mistake. I'll see, I guess, in the post editing process or whatever. But let's erase this and just go back through exactly the calculations that we did after this. 27.48. 27.48 is this angle here. 90 minus 27.48 gives us an angle here, which then gives us this angle here, which then gives us this, which then we can plug into here. And then this should give us an answer. Okay, so basically what I just said here is we found this angle. It is a new angle here. I'm going to do 90 minus this angle to find this angle here of this big triangle. And this big triangle will give us this angle here. So then we can do 180 minus 60 minus this angle to find this angle. And that angle we plug into here. A lot of angles. Of course, try doing this problem on your own and see if you get the same thing as me. All right, so what we got is 90 minus 27. Amazing. 27.48 equals 62.52. 62.52. 62.52. 62.52 degrees. And then we can do that 180 minus everything. So 180 minus 60 minus 62.52 equals 57.48. 57.48 degrees. That will give us this angle here, all right? Because that is this angle here. We don't actually want that. We want this angle here, which is 90 degrees minus this. And that angle we can plug into here. Alrighty. I got 90 degrees here minus 57.48 gives us 32.52. Is that this angle here? Yeah. All right, let's hope this works. 32.52. Delete everything. Sine inverse of 1.66 times sine of 32.52 gives us 63.17 degrees, which is here, which I will put here. 63.57 degrees. And that is the final exit angle with respect to the normal of this side of the prism for both of these. All right, we're good. Let's try erasing everything and finding the final answer here. So I'm gonna erase this since, I mean, there were some weird mistakes and stuff, and I still don't know if we have the right answer, but at least there's no alarm bells ringing of like weird stuff that doesn't make sense with the picture. And once we get the final answer, since I've done this problem before, I can kind of be like, okay, this looks like the final answer. But all right, let's draw the prism again. I'm gonna draw this little picture here. And what we found now was the red light, which I can draw here in a different color. So we have violet light is down here, boom, boom. And we have the red light, which does something like this. And then over here is the rainbow, theta spread. This is what we're looking for. Cool. How we found that was white light was entering here at some angle. And the angles that we found now were this one. From the normal to the red ray, this is red, is exactly 58.56 degrees. And from the normal over here to the violet ray, this is violet, is 63.57. So it kind of makes sense. 63 is a bigger angle than 58. So it makes sense that the violet ray is coming further down here because it's deflected at a greater angle. All right, so to find the spread, it looks like we could literally just take this angle and subtract this angle from it. The reason that works is you can imagine these two light rays are coming out from some point here. Maybe this is the side of the prism, and this is the normal here. So what we have is this angle and this angle, right? And we want to find this angle here. We could literally just take the big angle, subtract the small angle, and that will give us this difference over here. So my argument is theta spread is equal to big angle, 63.57 degrees minus smaller angle, 58.56, gives us this. Let's take a look at what it is. Plug it into the calculator, 63.57 minus 58.56 gives us 5.01. Oof. I don't think this is correct because when I did this problem, I found that the final answer for theta spread was 4 degrees, 4 point something. But maybe there was something related to how I plug numbers in. Maybe it was something related to significant figures or something like this. But anywho, if you don't have the solution, this is what I recommend. Copy paste the entire problem and hop onto ChatGPT And we're going to paste that bad boy in there. You could probably find a solution to this somewhere online as well, but if you can't, ChatGPT is a solid thing to use. Just keep in mind, it sometimes might get the wrong answer. So why I'm using it here is because I just want to see if my trajectory of solving this problem works. And if ChatGPT gives me an answer close to this, either we're both right or we're both wrong. And that allows you to later study this a little bit more and see where you went wrong. But for a first attempt, let's see. The angular spread of visible light passing through the prism is approximately 4.61. So this is our answer, and the ChatGPT answer is 4.61 degrees. All right, so my apologies. I maybe made a mistake here. Please take a look at the video. Try to see where this difference is coming from. But it is pretty close, like 1 degree off, 0.4 of a degree off. Not too bad. Maybe you could be a little bit more strict with your accepted error. But, and again, keep in mind, this might be something completely wrong with my entire process here. But this is how I solved the problem before. This is how I am solving the problem today. Please let me know if you have your own strategy for this. And also let me know if you spot a problem with my solution. That was an introduction on prisms, Snell's law, law of refraction. I'll post the problem again here if you want to try it out on your own. And thank you guys for watching. Peace.